So far, we've learned how to perform a significance test as well as create a confidence interval when we are trying to perform inference methods in order to find a population parameter. Specifically, we've been focusing on proportions, but today we're going to talk about comparing two separate populations. This can be a sample from one population and a sample from another. It could be taking two statistics from our two populations and comparing them to see if there is any growth. This is often what happens in experiments when you're comparing the group one that's receiving the treatment of a placebo and group two that's receiving the actual level of a treatment. So as far as the concepts, everything is the same. The calculations are slightly different because we're dealing with two sample statistics. So let's get started with that. The sampling distribution of a difference between two proportions. When we want to compare the populations or treatments with an inference method, we can look at the difference between the two parameters. So the statistics that's going to estimate the difference is one proportion minus the other. You're going to determine which one is population one, which one is population two, and that will come through your equations that we set up later on. But if we're looking at the difference between two, we want to subtract their proportions. That's going to be our sample statistic. So really quickly, here's a recap of everything from chapter 5 when we were talking about the sampling distribution, the difference of the sampling distribution of sample proportions. The center is the true proportion of those population, their difference, and the standard deviation equation is as follows. So remember, this is exactly from the last unit. This is a formula that you'll have on your formula sheet. So really quick, let's just kind of go through this example so we can make sure that we remember some of the concepts and we can inch in. Your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% crackers and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes an SRS of 50 crackers from bag 1 and a separate SRS of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportions of red crackers. So really quick, let's pull the important information out of that. Bag 1 has 25% red crackers. Bag 2 has 35% red crackers. So those are the true population proportions. So I'm going to say P1 for bag 1 is 25%. I'm going to say P2 for bag 2 is 35%. Right? The sample size, let's see, each bag contains more than 1,000 crackers. That's good to know. That's the true population. I can say capital N is greater than or equal to, we'll say greater than 1,000. But then it also tells us that bag 1 sample size is 50, bag 2 sample size is 40. So I'm going to write that up here. Sample size from population 1 is 50. The sample size from population 2 is 40. And that information is going to help me a little bit later. So what is the shape of the sampling distribution of the difference of the two proportions? Well, we can check the large counts condition. If we can check the large counts condition and they are both satisfied, then we know the difference will also be normal. So let's go ahead and check that. I'm going to take this information and move it down. It won't go with me to the next page, so I'll just minimize it there. So we have the probability, let's check P1, right? N1, P1 has to be greater than or equal to 10. And then N1, 1 minus P1 has to be greater than or equal to 10. So we have 50 times 25%. Is that greater than or equal to 10? Yes, it is. That's, let's see, 12 and a half. Half of 50 is 25, half of that is 12 and a half, yep. And then if I have sample size 50, 75% greater than or equal to 10, that is also true. I have 37.5. So large counts has been met for the first population. Let's check the second one. N2 times P2 has to be greater than or equal to 10, as well as N2 1 minus P2 has to be greater than or equal to 10. So sample size of 40 with the probability of success of 35. Is that greater than or equal to 10? Well, that's going to give us 14. In the same way, I need a sample size of 40 with a probability of success of 65%. Is that greater than or equal to 10? That's going to give us 26. So, since large counts is met for P1 and P2, then P1 minus P2 is approximately normal. All right, just kind of bringing back the information from the last unit. B is saying find the mean, also known as the center, find the center of the sampling distribution, show your work. So I know that my center, the center of P1 minus P2, that sampling distribution, is the true population proportions difference. So that is 25 minus 35, which the true center is negative 10%. All right, that comes from the formula earlier. C is telling us to find the standard deviation of the sampling distribution, show your work. So we know that the standard deviation of the sampling distribution of sample proportions, the difference in those, is the square root of those variances. So P1 times 1 minus P1 over N1 plus P2, 1 minus P2 all over N2. For us, that's going to give us the square root of 0.25 times 0.75 over 50 plus, now for our second population, 0.35 times 0.65 all over 40. Sum that up, square root it, you're going to get a standard deviation of about 10%, right? That's your standard deviation for that distribution. Right, just trying to remember how to describe the difference in sample proportion distributions. This is the information that you're going to need, right? We know it's normal with a center of negative 10% and a standard deviation of about 10%. Let's keep going forward. So our first inference method was confidence interval. When data comes from two independent random samples or two groups in a randomized experiment, the statistic p hat for the first population and p hat for the second population is our best guess for the value of the difference of the two populations' proportions. We're going to use the exact same method for calculating our confidence interval, the exact same method. So the conditions have to be the same, right? The conditions have to be met. The first one is that they are random. Don't forget random, right? Look for the word SRS. And that has to be for both samples, not just one. It has to be for both, right? We still need to make sure that it's independent. Right, using that 10% condition, make sure we're dealing with less than 10% of the population, and large counts. And just like we did earlier, you need to check it for both distributions. So N1, P1 has to be greater than or equal to 10. N1, 1 minus P1 has to be greater than or equal to 10. N2, P2 has to be greater than or equal to 10. And N2, 1 minus P2 has to be greater than 10. If all three of those conditions have been met, then we have the exact same formula. We have our statistic plus or minus the critical value times the standard deviation of the statistic. Remember, all of this is known as the margin of error. All of that is known as the margin of error. This is going to be your Z statistic, Z star. This is also known as SE, the standard error of the statistic. So let's move on. Two sample Z intervals for the difference between two population proportions, right? Giving that a little more information. The statistic is the difference of the two samples that we collect. The critical value is still that Z score. That standard deviation of the statistic is the same as what we talked about in the last unit, as well as a few slides ago. This is what we're going to use to calculate our confidence interval. So let's do an example. As a part of the Pew Internet and American Life Project, researchers conducted 2 surveys in 2012. The first survey asked a random sample of 799 US teens about their use of social media and the internet. A second survey posed a similar question to a random sample of 2,253 US adults. In these 2 studies, 80% of teens and 69% of adults use their social networking sites. So A says, calculate the standard error of the sampling distribution of the difference in the sample proportions, teens minus adults. What information does this provide? So let's calculate that standard error. Remember, this is the standard deviation of the statistic. Those are the 2 different ways that we can word that. Standard error is the standard deviation of the statistic. So let's start with that. Well, we remember that the standard error for one proportion minus the second proportion from 2 populations is that square root of probability of success. But remember, we need to use the information that we collect from our sample. Let me write this all out. Right, it's that same formula. The only thing that's different is instead of using the true population proportion, which we don't know, we're going to estimate by using the sample statistics that we've collected. So plugging in all the information that I know from teens minus adults, right? We're doing teens minus adults. That means P1 represents teens. I know 80% of teens, so 80 times 20, over a sample size of 799, because that was the sample size for teens, plus 69% times 31% over 2,253 adults. That was the sample size for the adults. Throwing that into our calculators is going to give us a standard error of almost 2%. So 1.72%. So what information does this provide, right? If we were to take many random samples, I'm going to say if we took many random samples, the difference in sample proportions would typically be 0.0172 from the true difference. The true difference in proportions of all teens and adults who use social networking sites. I'm not going to write that all out, but just to give a little more context to that, if we took many random samples in the difference in the sample proportions of teens and adults who use social networking sites, it will typically be 0.0172 from the true difference in proportions of all teens and adults who use social networking sites. It's a mouthful, right? Just tried to condense it as much as I can. B says, construct and interpret a 95% confidence interval for the difference between the proportion of all US teens and adults who use social networking sites. Well, this is an inference method. So before we even begin, we need to follow our process. I need to state what I'm doing. So I'm going to do a 2 proportion confidence interval. All right, 2 proportion confidence interval. You could say the difference of 2 proportions confidence interval, right? And we know all of our information. We've already talked about it, but I need to check my conditions. 1, is it random? You can say yes. An SRS of 799 teens and 2,253 adults were collected. Are we dealing with less than 10% of the population? Well, we can assume more than, remember, take the sample size, add a 0. We can assume more than 7,990 teens use technology in the US, and more than, take the sample size, add a 0, 22,530 adults use tech in the US. So we've dealt with the independents. Now we need to check the large counts, right? I can say 799 times 0.80, is that greater than or equal to 10? Is 799 times 20% greater than or equal to 10? Is 2,253 times 69% greater than or equal to 10? As well as 2,253 times 31% greater than or equal to 10. I'm not going to do the math, but yes, all of those work, right? Remember, that information is coming from here, where those numbers are coming from. So we've met all 3 conditions. Now we can actually run the critical value. So I know that my statistic, remember, it's the statistic plus or minus the critical value times the standard error, or the standard deviation of the statistic. So let's go based off of the sample that we've collected. This I'm going to have to actually go back and look at my information. 80% of teens and 69% of adults. So I'm doing teens minus adults, so I need to do 80% of teens minus the 69% of adults, plus or minus the critical value. Remember, we're doing a confidence interval of 95%, so that's 1.96 as our critical value, times the standard error of the statistic, which for us, we calculated in the previous problem, so I'm just gonna substitute that in, 0.0172. We can do this math and simplify it. We've got 11% plus or minus 0.034. So we've got a margin of error of about 3%, right? We're going to have the confidence interval of 0.076 to 0.144. How would I interpret that, right? Interpretation is very important. We are 95% confident that the interval from 0.076 to 0.144 captures the true difference in the proportion of all US teens and adults who use social network sites. I'm just going to say social media. That's how we would interpret that confidence interval. If you want to use the calculator, you're going to use the 2 proportion Z interval. That's what it would look like on the calculator, the 2 proportion Z interval. Everything follows the same. I'm not going to put time in this video to show you how to do that. If you've got questions, let me know, but you still go to menu, you go to the tests, you find the 2 proportion Z interval, that's for the 84, and Spires, you go down to confidence interval and select 2 proportion Z interval. So let's shift gears. Let's change from confidence intervals to significance tests for the difference of population proportions. An observed difference between the 2 sample proportions can reflect an actual difference in the parameters, or it just may be due to chance that the variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has this general form, that the difference between the 2 is some hypothesized value. Now, think about it. If you're creating an experiment and you're experimenting with a new pharmaceutical and you want to compare the proportion of white blood cells that are collected in a sample of total blood cells, right? And you want to make sure that they're the same, otherwise the medicine may be bad to give to patients, right? You would want the difference in those proportions to be 0. So that's often what we do, is we say that the difference of my 2 samples is 0. I can do some math, right? If I add P2 to both sides, another way of saying is the null hypothesis is that the 2 proportions are the same. This is the one that we are going to go to most often, right? There is no difference in the proportion of white blood cells that is being counted out of the total blood sample between red versus white. So our alternative hypothesis is that they're different. Remember, this is 2-sided. You're often going to do 2-sided with differences. You could do 1-sided, but most often you'll do 2-sided, right? The probability that they're different. So these are the null and the alternative for the difference of 2 proportions when performing a significance test. So again, the conditions are the same, random, large counts, and the 10% independence. And we still have the same concept for our test statistic, right? The test statistic is just like a z-score, the statistic minus the parameter over the standard deviation of the statistic, right? Just like a z-score. However, it looks a little different when we're doing a difference in proportions, right? The statistic that we're collecting is the difference of the 2 samples that we've collected. We're assuming, right? We're assuming the difference is 0, just like we did up here, right? We're assuming that the difference is 0. So we're assuming that the new center is 0 divided by the standard deviation of the statistic. However, we run into an issue when we need to calculate the standard deviation of the statistic. So we have a new concept that we're going to start working with. If the proportions are equal, if that null hypothesis is true, the 2 parameters are the same. So we call their common value P, the proportion P, but we need to figure out a way to estimate that. So what we're going to do is we are going to imagine the 2 samples that we collected come from the same population and therefore make the same sample. And so we pool or we combine the samples. The pooled or the combined sample proportion is the number of successes in both samples combined divided by the count of both sample sizes, right? This is not like regular fractions. This is just taking those values and adding them together. This is not like adding two fractions. So for example, if we were talking about marbles in a jar, and we're talking about the proportion of blue, say my first sample, I get 7 out of 10 being blue. Let's say now I'm talking about a different jar of marbles, and this time I'm talking about red, right? And let's say that my sample for this second one is 3 out of 8. Let's say there were only 8 marbles. Well, if I want to combine these two sample statistics, I would just say 7 plus 3 over 10 plus 8. This is going to give me 10 over 18, right? Not like adding regular fractions, we're just adding the numerators and the denominators. This is my combined sample statistic. This is what I'm going to use when I want to calculate the standard deviation of the statistic. So let's look at the formula. This is the two sample z-test for the difference between two proportions. That test statistic is the same as before. The statistic minus the parameter, which we're assuming is 0, divided by the standard deviation of the statistic. But notice how I'm using the pooled sample, the combined sample. These are still relative to the sample sizes, the two sample sizes that we're using. But this statistic is coming from the combined two statistics put together. So we, like I was saying earlier, we could use a one-sided alternative hypothesis if need be to show that something is giving an improvement, right? That depends on your experiment. Think of an experiment where we're testing to see if a scarecrow actually does help preserve crops from birds, right? I can test the proportion of corn eaten having be less than the corn eaten without a scarecrow, right? I could say that my alternative hypothesis, proportion 1, is less than proportion 2, right? We can say with scarecrow. We could say without scarecrow. This is the experiment that we can run. If it is true, that's how we can have an experiment show that there is a causation. So let's do this example really quick. We've got 2 examples that I want to go through before the end of this video. High levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate. The volunteer subjects were assigned at random to one of 2 treatments. 2,051 men took the drug gemfibrozil to reduce the cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, 56 men in the drug group and 84 men in the placebo group had heart attacks. Is the difference statistically significant at the significance level of 1%? Right, we're dealing with the health of people. It is giving us a significance level of 1%. So we're not going to use 5, we're going to use the 1. And now we need to run a significance test. So let's state everything that we need to do. What are we doing? We are running a significance test. In the difference of 2 proportions. I need to state my null hypothesis. Well, my null hypothesis is that the group, the proportion of people who had a heart attack for the pharmaceutical group and the placebo group, we're going to assume that there's no difference, right? So P1 is equal to P2. The alternative is that the proportion of people who had a heart attack with the drug was actually less than those on the placebo. Let me write this over here. P1 is the proportion of men on the drug who had a heart attack and P2 is the proportion of men on the placebo who had a heart attack. So the null hypothesis said, hey, there's no true difference in the proportion, right? The alternative says, hey, the people on the drug, the proportion actually decreased, right? This is where it's going to be one-sided. This is what we're looking for. And we were told our significance level is at 1% because we're dealing with the health of people. So I've stated what I'm going to do. I've defined some variables so I know what P1 and P2 stand for. I've stated my hypotheses and I've stated my significance level. Now I need to plan. I need to plan and actually check my conditions. So let's see if we come from random. Is it random? We can say the two groups are random. And how do we know this? Well, because it tells us, right? They were the Helsinki Medal of No History. The volunteers were assigned at random to different groups. So because it was randomized, we can actually go through with a random condition. Let's check the independence, right? That's also known as that 10%. Well, if we want to do the 10%, there was no sampling here, so technically we don't need to check the independence, right? Because there is no sampling here, we don't need to check this. Right, we checked every single person in each group. So we don't need that 10%. The independence only shows us independence in a random selection. We checked everyone. Now we have to check large counts, right? We can go through and check the large counts. I'm gonna save some time and just say that this has already been met, but you will need to show the large counts. So let's go ahead and actually do the work here. So let's do P1, right? For the people who did take the drug, we know that 56 out of the 2,051 had a heart attack. That is 2.73%. And I know the placebo group, the statistic that I collect, 84 out of those 2,030 had a heart attack, which is about 4%. That's the placebo group. So I need to find the pooled or combined proportion. Your calculator will automatically do this for you, but that's going to be 56 plus 84 over 2,051 plus 2,030. That's going to give us a total of 140 over 4,081. My pooled statistic is about 3.5%, a little bit less, 3.43%. So what does that mean? What am I doing? We can use a calculator to help us do this. Using a calculator would be the best way. If you wanted to do it by hand, you could say that the test statistic is P1 minus P2 minus 0, right? All divided by And then I'm not even going to fill everything in here. Just remember, this is the PC1 minus PC, a lot of fractions, right? Over 251 plus PC. This is a lot of work. You won't do any of this. You're going to do all of this on your calculator. That test statistic comes out to be 2.47. So if I'm thinking of a distribution, a standard normal distribution centered at 0, thinking of the negative 2.47, thinking of that negative value, I want all the area to the left, because remember, my alternative hypothesis is saying that the proportion of men who took the drug is less than those who took the placebo. So I need to find the area in the curve there. Using a calculator, you're going to get a p-value of, let's see, 0.00675, so on and so forth, right? So let's take this p-value, let's assess it against our significance level of 1%, because our p-value is less than 1%, less than alpha, less than our significance level. We can reject the null hypothesis and assume the drug, the pharmaceutical, reduced heart attacks in, remember the population, middle-aged men. And we're done. There is one more example. I'm going to go through and do the next example. You don't have to stay and finish watching if you don't want to. I'm going to do it just so that there's more exposure and more examples to this. If you're looking how to do this on a calculator, let me go ahead and show you quickly how to do it on a calculator. I'm going to start with the NSPIRES menu, statistics, stats test, a 2 proportion z-test. You're going to input all of your information, your first sample, your second sample, and your alternative hypothesis. If you want to do that confidence interval really quick, stats, confidence interval, 2 proportion z interval. Same information, adding your confidence level. If you are doing this on an 84, you're going to go to stat, you're going to go over to tests, you're going to see that there's the 2 proportion z-test, number 6. If you need that confidence interval, just keep going down. You'll find there's the 2 proportion interval. Just like that, you insert the same information that is needed. So if you want, you can peace out. I'm going to do the other example problem really quickly. So let's see what we're doing for this one. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, an SRS of 150 included 26 who had not had breakfast. More than 1,500 students attend each school. Do these give convincing evidence at the significance level of 5% of a difference in the population proportions? So let's go ahead and run our test. I am going to state what I'm going to do. I'm doing a 2 proportion significance test. My null hypothesis is the proportions are not different, right? I'm going to assume that they're the same. I'm going to say P1 is the first school, P2 is the second school. I don't really need to write that out. My alternative hypothesis is that Oh, I'm sorry. My null hypothesis is that they're the same. There's no difference. My alternative hypothesis is there is a difference. My significance level is 5%. Now let's check my conditions. Is it random? Yes. SRS of 80 and 150 students. So I know that it is random. I can check, is it independent? I can say yes, more than 800 and 1,500 at each school. How do I know that? Because it tells us. For the second sample, right, for the second sample, it is 1,500. That's why it has to be less than or equal to 10%. So we're still solid there. And now we need to check the large counts. I'm going to save some time, but, right, N1 times P1, is that greater than or equal to 10? N1 times 1 minus P1, is that greater than or equal to 10? N2 P2, N2 1 minus P2, are those greater than or equal to 10? Right, checking those, they are, just to save some time, I don't want to go through them. So we've planned everything that we need. Let's go ahead and do the work. Right, I know that for my first school, 19 out of the 80 didn't eat breakfast. And I know for my second school that 26 out of the 150 didn't eat breakfast. So when I want to find the test statistic, right, you do want to write down the test statistic. The test statistic is 19 over 80 minus 26 over 150, that minus 0, over, and now I need the pooled statistic, which is 19 plus 26 over 80 plus 150. That is going to give us 45 over 230, which is about 19.57%. Get rid of that decimal, 19.57. Right, I'm going to do the standard error using that value. And instead of writing it all out, well, I'll write it out this time. Right, we have 19.57 times 1 minus 19.57 all over 80 plus 19.57 times 1 minus 19.57 all over 150, right? Plugging that into our calculator, we are going to get a test statistic of 1.17. So really quickly, think of a normal distribution centered at 0 based off of our null hypothesis. I want to find 1.17 on either side. Right, one's negative. I want to find the area on either side of my distribution. This is going to make up my p-value. Use a calculator to get your p-value. You're going to find your p-value is 24%, about 24%. So we can say because our p-value of 24% is greater than alpha, we fail to reject the null hypothesis. I can say there is not convincing evidence that the true proportions of students who did not eat is different. Or are different. And there you go. With that, you know how to perform a significance test and construct a confidence interval for two proportions.